Hello everyone, welcome to Basics e-learning.
Electronic devices and circuits is the first year common subject in BTech irrespective of branch. EDC or SDC introduces an engineering student to the basic electronic devices, circuits and its operation. If you are in ECE, electrical or instrumentation engineering, you must thoroughly understand the basic concepts so that you can better deal with the subjects that you are going to face in further semesters. Just do watch the video carefully and understand the basic concepts easily. In lesson number 1 video, I am going to discuss what is a semiconductor, what are the properties of a semiconductor, its classification, what is intrinsic and extrinsic material, how is this P-type and N-type semiconductors formed and their energy band description, why you are using a semiconductor in electronic devices. So all these topics I am going to discuss in lecture number 1. Let us see what is a semiconductor. Semiconductor is a material that has the resistivity that lies between conductor and an insulator. We know the materials are divided into three types: conductors, insulators and semiconductor. Conductors are the materials which will allow the current to pass through. Example: copper, aluminium, gold, silver, right? So aluminium, gold, silver, etc. Coming to insulator, they will not allow the current to pass through. Example: wood, glass, plastic. Coming to semiconductor, they have their conduction properties, that is in between conductors and insulators. So the conductivity of or the resistivity of such materials is given by 10 power minus 4 ohm meter to 0.5 ohm meter. Examples of semiconductor are germanium, silicon, selenium and carbon. Let us see the properties. The resistivity of a semiconductor lies less than an insulator but more than a conductor. Right, that is what I have discussed in the definition itself. Here, the second property is they have negative temperature coefficient of resistance. Let us see what is this negative temperature coefficient of resistance. As the temperature increases, the resistance of the material decreases. We'll see how it is. Any material, the atomic structure is defined, predefined, right? So any atom here. Now, according to the atomic structure, the last band we call it as valence band. Once this valence band electrons or the charged particles gets the energy, it will release and then jumps into conduction band. So as the temperature increases, the valence band electrons will get proper energy and will jump onto the conduction band. Now they'll become free electrons. So as the temperature increases, the number of free electrons in a material increases. So the conduction increases. As the conduction increases, the resistance decreases. So this is how the semiconductors have negative temperature coefficient of resistance. And the third property here is when a suitable metallic impurity is added, the current conducting properties changes drastically. So the impurity atoms like arsenic, gallium, etc. are added to the semiconductor like germanium or silicon. The conductivity properties of these semiconductors changes. This is very important property and we are going to discuss more about this property later. Let us see the classification of semiconductors. We know the materials are divided into three types: conductors, insulators and semiconductor. Coming to semiconductor, semiconductors are again divided into two categories: intrinsic semiconductor and extrinsic semiconductor. Intrinsic semiconductor is the extremely pure form of semiconductor. Example are germanium and silicon. In these type of materials, number of electrons, Ne means number of electrons, is equal to number of holes. Coming to extrinsic semiconductor, we are adding a suitable impurity to the intrinsic semiconductor to make an extrinsic semiconductor. As I discussed the third property there, the conductivity properties of a semiconductor changes when we add an impurity. So if you add an impurity to a pure semiconductor, that results in an extrinsic semiconductor. So depending upon the impurity added, they have divided into two categories again, N-type and P-type. So if we add pentavalent impurity to an intrinsic semiconductor, the resultant extrinsic semiconductor is called N-type semiconductor. Whereas if you add trivalent impurity to an intrinsic semiconductor, we will get a P-type semiconductor. The examples of pentavalent impurity are arsenic, antimony, etc. Coming to trivalent impurity, gallium, boron. Donor impurity we call, the pentavalent impurity we call it as a donor impurity, whereas the trivalent impurity we call it as an acceptor impurity. In N-type impurity, N-type extrinsic semiconductor, the number of electrons are more than number of holes. Whereas in P-type semiconductor, the number of holes are more than number of electrons. Let us see what is an N-type semiconductor. When a small pentavalent impurity is added to a pure semiconductor or an intrinsic semiconductor, the resultant is an N-type semiconductor. Now let us see how this N-type semiconductor is formed. Consider a germanium crystal in its pure form. Germanium, which has an atomic number of 32. The atomic distribution is 2, 8, 18 and 4. So the valence band has 4 electrons. See, this is the germanium atom which has 4 electrons. So it is occupied. Covalent bonds are occupied. So the pentavalent impurity that is added to the germanium crystal is here arsenic, which has the atomic number of 33. Atomic distribution is 2, 8, 18 and the remaining is 5. So the last valence band has 5 electrons. What happens here? The 4 electrons are combined with the covalent bond. The remaining 1 electron is left here. So this 1 electron left is the free electron. When a small amount of pentavalent impurity like arsenic, when you are adding to a germanium crystal, one electron is left over. That is the free electron. So arsenic is pentavalent. That means 5 valence electrons. So that's why this arsenic, we are calling it as a pentavalent impurity. So when a small amount of this pentavalent impurity is added to this germanium crystal, it is releasing number of free electrons. So these free electrons will make a large supply of more and more free electrons. Coming to the energy band description of this N-type semiconductor. So the addition of a pentavalent impurity which has produced number of free electrons. So the free electrons will be in the conduction band here. The four valence electrons of the pentavalent atom form the 4 covalent bonds with the neighboring germanium atoms here. But 1 electron is left over, that is free electron that lies in the conduction band here. So the more new free electrons are produced in addition of because of the addition of here pentavalent impurity. So even at room temperature it will form whole electron pairs. But the domination of electrons here makes the number of electrons in this N-type semiconductor more compared to the number of holes. So that's why the N-type semiconductor here, N stands for negative. The predominant nature of electrons over holes makes the semiconductor as N-type semiconductor. Let us see how the P-type semiconductor is formed. When a small trivalent impurity is added to a pure semiconductor, the resultant is a P-type semiconductor. We will see now. So let us consider a germanium crystal again, which has the atomic number of 32. So the atomic distribution is 2, 8, 18 and 4. Whereas for, let us say here, the pentavalent impurity, sorry, the trivalent impurity that I am taking is gallium, which has the atomic number of 31. Then the atomic distribution will be 2, 8, 18 and 3. See now, for this germanium crystal, I am adding one gallium atom, right? So the gallium atom here, it has 3 valence electrons. So the 3 valence electrons makes 3 covalent bonds with the corresponding or the neighboring germanium atoms. One covalent bond is not formed, right? So which makes a space here, right? So that we call it as a hole. The missing electron here, we call it as a hole. So gallium is a trivalent, means it has 3 valence electrons. So each atom of gallium first try to fit into the germanium crystal. But what happens here? There are only 3 full covalent bonds formed. So the 3 single covalent bonds are formed, but the 4th covalent bond is in this one electron is missing. So the missing electron, we call it as a hole. So a small amount of gallium provides millions of holes here. So the domination of holes in the semiconductor after adding this impure material, the trivalent impurity. So the number of holes are more here. That's why we call it as a P-type semiconductor. So as it has one hole, it is always ready to accept the new electron. So that's why we are calling this as acceptor impurity also. Coming to the energy band description of this P-type semiconductor, after adding a trivalent impurity to the pure germanium crystal, we have seen the resultant is with more and more number of free holes here, right? So the missing of electron, we are calling it as a hole. Though the crystal is kept at room temperature, few of the electrons will recombine with the holes, but you have large number of holes. So here, as there are more number of holes, so the predominant nature of holes over the free electrons makes the semiconductor P-type semiconductor. Here P stands for positive. Let us discuss why we are using semiconductors in electronic devices. So the major property of the semiconductor makes the use of the material in manufacturing electronic devices. That is, when you add a small impurity to a pure semiconductor, the conductivity properties of the semiconductor changes drastically. That is the main reason. Other than that, the advantages here are it has less weight and smaller size compared to the previous versions. They are valves, right? So electric valves are the tubes that is constructed with a glass structure and bulky. Coming to the semiconductor material, the size is very less. And similarly, no power for the filament. If you see the tube, you have a filament and a cathode. So initially to start, we need the power. Here, there is no need. Compared to the tubes, the semiconductor material have longer life and also ruggedness. Power losses are also less and it requires less supply voltages.
For more videos, please do like, share, subscribe to our channel. Let us know your suggestions and queries in the comment box. Thank you.